In this video, we'll delve into the fundamental concepts of simple and multiple linear regression, essential tools in statistical analysis and data modeling. Linear regression is a statistical method used for modeling the relationship between a dependent variable and one or more independent variables. It's a cornerstone of data analysis, helping in predicting outcomes, understanding relationships, and driving decision-making processes. Simple linear regression has only one independent variable, and multiple linear regression has more than one. The core idea of linear regression is to find the best fit line through the data points. This best fit is achieved by minimizing the distance between the data points and the regression line. These distances are known as residuals, and minimizing them leads to the most accurate model for the sum of squared residuals. Notice the point illustrated with a difference between it and the line of minus 1.32. The difference between that point is squared along with all of the other points and added up. The line that is drawn such that the sum is as small as possible has the best fit. More complex relationships require more variables to explain. In this case, we add a binary variable that shifts the y-intercept when it equals 1. Let's use some illustrations by Allison Horst to explore the interpretation of linear regression. Allison has determined that the weight, in tons, of a dragon is 2.4 plus 0.3 times the height. 2.4 is the y-intercept. It means that even a dragon with no height has a weight of 2.4 tons. Of course that is not true, but this line is the line that best fits all of her data. And she probably did not observe any dragons with a height of 0. For every foot of height of the dragon, we would expect 0.3 tons of weight. It turns out that spotted dragons are more dense than striped. Spotted can take on a value of 0 for not spotted, or 1 for spotted. When multiplied by the coefficient, we see that striped dragons are heavier. Putting the two pieces together, we have an equation that we can evaluate to predict the weight of a dragon by its design and height. But it is likely that the observed dragons did not weigh the same as is predicted by the line. We find the residual by taking the difference between the predicted, denoted as y hat, and the observed height, denoted as y. Remember, the point is to find the line that best fits. It will not fit perfectly. We would expect that if we plotted a histogram of the residuals for them to be normally distributed. As illustrated, close to normal works with real data.
The previous announcer was once again sacked.
The Gauss-Markov assumptions are key to ensuring the best linear unbiased estimator in the context of ordinary least squares regression. The linearity in parameters assumption states that the relationship between the independent variables and the dependent variable is linear in the parameters. This means that the model is a linear combination of the parameters' efficients, but it doesn't rule out nonlinear relationships between the independent and dependent variables like polynomial terms. In practical terms, this ensures the model can be accurately estimated using linear regression techniques. The random sampling assumption states that the data used in the regression model should be a random sample of the population. This assumption is crucial for the generalizability of the model's conclusions. In practical terms, it avoids selection bias and ensures that the model's findings can be extended to the broader population. The no perfect multicollinearity assumption states that there should not be perfect multicollinearity in the model. This means that no independent variable is a perfect linear function of other explanatory variables. In practical terms, it ensures each independent variable brings unique information to the model, allowing for the estimation of its specific effect on the dependent variable. The conditional mean of errors is 0 or exogeneity. Assumption states that the expected value of the error term conditional on the independent variables is 0. In practical terms, the guarantees that the independent variables are not correlated with the error term, preventing biased and inconsistent estimates. The heteroskedasticity assumption states that the variance of error terms is constant across all levels of the independent variables. If the variance changes as pteroscedasticity, it can lead to inefficiency in the estimates and effect hypothesis. The practical implication is that this prevents underestimating the standard errors, leading to more reliable confidence intervals in hypothesis tests. It's important to note that while violations of some of these assumptions can be addressed, for example, through transformation of variables or robust standard errors, they form the bedrock of reliable and valid linear regression analysis. The Gauss-Markov theorem asserts that if these assumptions are met, the OLEST estimator is the best in the sense of having the lowest sampling variance among all linear unbiased estimators. We've just scratched the surface of linear regression. As we progress, we'll explore these concepts in greater depth, learn how to implement them in practical scenarios, and understand how to interpret the results.